Okay. So the next talk is by Karol Kampf from Prague, and he will tell us about the theory perspective of the low energy QCD. Please.
Thank you very much. Thank you for giving this possibility to talk this very interesting place, and apology for presentation, but yeah, it's kind of exotic, so I hope you don't mind. I would like also thank Shruti because she introduced some of the technical details. I can be faster. So we heard a lot of, or you heard a lot of this workshop about new variables to describe N=4. So let me say it will be much simpler here because in principle we don't need any new variables, and we just need Sij pi.pj. Because I will try to describe these theoretical methods, the amplitude methods for scalar theories. I will try to, at the end, we are physicists, so we would like to, or we would dream of using any theoretical ideas for physical theory. So I will try to add my perspective, as I put to the title, also how we are standing, how it is possible to say something about experiment or connection to experiment. So it will be basically mostly overview, very quick overview, and first slides, it's not only to introduce to the subject, but also to move me back 10 years ago when we started with Yara and my collaborator to think about this possibility. So let me skip this amplitude. So we know that we have a way. I mean, it's probably, I will say it anyway, it's important to realize that if you are especially new to the subject, that we are, in principle, looking for something which we know how to calculate. This might be sometimes strange to realize why, if we know how to calculate, why we bother. So we have the way via Feynman diagrams, for example, to get to the result. But as you hopefully learn at this workshop, it's still useful to find another way because it can enlarge the situation. It can find you some surprises to discover new properties and symmetries. So the best example to show is this QCD gluon amplitude for MHV, which using the standard model or usual Feynman diagrams calculation is very tedious, and yet, as was discovered, the final result is simple. For this MHV amplitude, even not trivial, but it's super simple. And this was basically, as I said, I summarized these steps, which is cyclicity, eventually BCFW reconstruction to get to this result. It was the starting point for us. This was the knowledge, and we said, okay, let's try to implement it for pions. So I'm grateful again to Shruti because she mentioned explicitly how this BCFW gives you only one diagram basically for this MHV amplitude. So it's not very hard to see why it is useful for this Pargen-Taylor result. So the lesson learned from the previous similar studies is that we have to know about relevant degrees of freedom. So for example, for gluon, you don't see any fermion because they are subleading, let's say. So you have to focus, you have to simplify the problem you are studying. So this is one lesson. Another lesson, very important. Of course, gluon are massless, and they were always massless. But if you want to study pions, kaons, and scalars, they are in principle not massless. But as a first step, it is reasonable to take them massless. But the big question was: is it even possible to extend it to effective field theories? Because so far, that time we studied it, it was only possible for renormalizable theories. And we were not even sure whether NLSM I will speak in a few slides what I mean by this shortcut. What is it? If it is the correct theory, we were open to just to find some theory to play with and to use some known tricks from amplitudes also there. So NLSM, there is of course huge prehistory connected with really great names connected with particle physics. So it seems it's a nice theory to study. And as I said, it's more than 10 years when we open this problem or reopen this problem from new perspective. Sometimes today there are words like soft bootstrap, so this will be like 2/3 of my talk will be for. I will try to focus to redo this. Yeah, so you can read all what was in our mind that time, and I think I said most of it strictly massless. So again, I repeat, those pions are now massless. We heard about spontaneous symmetry breaking in the morning, and we know this is like the slide which summarized this standard structure. You ask what I meant by this, what I mean by this NLSM. So this is a textbook's explanation of how to get to this Lagrangian from the symmetry breaking pattern, and to which describe the dynamics of the Goldstone bosons. As we had in mind that it is simpler to work with the order diagram, we do the first things which should be possible. We try to strip the vertices. Again, how it is possible, what kind of group it should be, we were again, as I said, open, and it seems it looked like the most simple choice is SUN group, because first of all, this is the physical model, or the closest to the physical model is SUN. And thanks to the completeness relation, it was easy to explain why the stripped, why the single trace operator is crucial for the amplitude. So this is, it's not only to show off what we did, but it's also, again, another lecture to show some technical details, not for the technical detail itself, but to show you what we were struggling. So we were not sure whether we find some way how to implement this amplitude method. So first we were like trying to use everything possible and trying to find technical way how to calculate the amplitudes, to get the data, to have the available theoretical objects to study. So we know that there is something like exponential parametrization, but as it is clear from the name parametrization, there might be some other parametrization. So we said, okay, let's try another parametrization. Usually, if you calculate something and you use different parametrization, you end up with the same result. It's used just for the safe purposes, to be sure that the result is correct. It's up to your choice to use some. Of course, some of the parametrization can be easier for calculation. Some of them could be not so. It could be more problematic. But at the end, the result should be the same. So we did all these details you can find in the article. But as I said, this is not to show the details. You don't need to know it. It's only important to realize it is there. And the lesson which you can also take from that very recently it was again reused. For example, in this Nima, I will get to that. He rediscovered this minimal parametrization, or how we call it the square root parametrization. It's very useful for his purposes. So you never know when or how these technical details might be important. But for us, that time we were just looking for calculation, and we wanted to prove something. And for us, that time it was more important, for example, the Cayley parametrization. It had some properties, and then it was possible to extend some proof of the property. Okay, so now you have all technical details, you have several details, you have several parallel possibilities how to do it. So now you can calculate the stripped amplitudes, similar to the gluon amplitudes. So 4-point amplitude is this. So you can picture it like scattering of 4 pions, something which is really measured in experiments. But you can continue and you can calculate 6 pions, so it would be more problematic. Of course, as a picture, Feynman diagrams, it looks much simpler. This is the full result, but of course, as we know, it's cyclic. Very often we can make it shorter using this cyclic notation. Okay, still not enough. 8-point, and I think we were the first who calculated 10-point on. And I think we added also 12-point, etc. So these are the diagrams to calculate. So these were the data using how to call standard method that time available. And even for that, we had to somehow invent it, some technical details. So what is soft bootstrapped in this sense? So we know there is a basic property coming from this, I didn't stress it, this overview, but there is a basic property of Goldstone boson, and is this soft or Adler zero property. So let's forget about the Lagrangian and let's try to do it via amplitude. So what does it mean? So you have, for example, this 6-point amplitude is the first non-trivial order which mix 2 different vertices. This 4-point vertex and 6-point vertex. And just roughly the power counting, this is some constant lambda, and this is some constant lambda 6. And the power counting is, this is OP square, this is OP square, and this is OP square. But there is a propagator, so these 2 constants, if we cancel, this is just the power counting, it's not the result. But as a power counting, we see this lambda 4 square should talk to lambda 6. And of course, as we know from this property, the property which can make it explicit, this connection is this soft limit. So the amplitude should vanish. These 2 terms, or I mean, there is several terms which correspond to all those diagrams. If we go with one momenta to 0, first momenta, let's say P1 goes to 0. It should vanish. So it should somehow give you the property, if you don't know the Lagrangian which is behind it, but you are just as generic as possible, there should be some connection. And this soft limit somehow naturally opened this connection. But this was 6-point, and of course the question is how we can use it automatically up to all orders, and this is what we can call recursion relation. But first, we need this soft we need these shifts as we heard, and the reason is, as we heard, due to bad behavior at infinity. So it doesn't go as 1 over z. It doesn't vanish in infinity. So we have to use different way, and the trick was this on-shell all line shift. Sorry. Why it works? Because it helps the behavior in the infinity. You can use the property of Adler zero, and you can put it into the denominator, and it definitely helps the high energy behavior. If it helps enough, you have to, of course, to work out the power counting, but it does. So it opens completely new territory on this. it doesn't need to be used. It doesn't need to be used only for calculation of an LSM, but now it could help you to bootstrap any amplitude. What does it mean? Any amplitude. So you can, in some sense, classify what kind of amplitudes it can reconstruct. So we have this parameter sigma, as we already heard. It was written, I think, here, which tell you how quickly it goes to zero. And naturally, we should also have another parameters which tell you, roughly speaking, what is the power counting or how many derivatives there are in the Lagrangian. So in some sense, this rho parameter is somehow averaging number of derivatives. So if you have terms with 4 point with m derivatives and 6 point with some m tilde derivatives, somehow the same rho will make sure that these two diagrams talk to each other. And another important trick is that it somehow, the interesting theories are those which make it which make some cancellation among the diagrams which are of this order. So if you have, well, I don't know, 100 derivatives, it's of course not such a big deal to vanish. But if you have the critical number of derivatives, so you need terms among themselves to kill each other. So you have some interesting soft limit. So and this table summarizes this that you have a rho equals 0. Just rho equals 0 means we have two derivatives. M is number of derivatives. For 4-point vertex, we have two derivatives. So it corresponds to the old NLSM. So it should behave as O1, but you can continue with other theories, which again Shruti summarized already. You know the result. So I can be very quick here. For rho equals 0, you can prove that the only theory is really this NLSM. For rho equal 1, you can is an interesting not that complicated game. You can write. So now you have one derivative for each field. You can again write our favorite 6-point diagram and do the calculation and see how it can make this other 0, this sigma equal to 0, so-called double soft limit, and you can easily check that this would be the condition. And you might ask, okay, what is the symmetry behind this? So it's again easy to show explicitly. You can even do the simple algebra to predict what kind of theory it will give you, and the answer is as we already heard, DDI. Rho equal 2, sigma 2. So I'm going back to the table. So we did this one, and now we are at this point. I think I have a mistake in the table, so I'm rather not going back. So this is this Galilean theory, and again you can repeat the same steps and get the explanation of the symmetry. So we were rediscovering the known theories from bottom up using this soft bootstrap. And fortunately, we were quite lucky because we also discovered a new theory for this. Rho equal 2, sigma equal 2. You have several constants. Here several constants. So it's natural to increase the soft behavior by one order, and ask if there is a theory which has this property. It should work among those Galilean theory, and in fact, it's possible. There is theories as you know, special Galilean, and unfortunately, we were not that smart. We didn't discover what is the symmetry behind it. So it was a few weeks after we published it. It was found, and of course, as you also already heard, it was independently discovered also by CHY mechanism. Okay, so this is the so-called classification of soft classification of scalar theories from the soft bootstrap point of view. And if you like picture, this is our summary of these theories. Okay, I have still some minutes, and I have still 10 pages to go. So, what could be the extensions of this work? So, of course, it's all the simplification we made at the beginning, and we must be asking. So, big simplification, the massless of pions. We of course know that pions are pseudo-Goldstone boson. They are almost Goldstone boson, but they have their mass. So there is some explicit symmetry breaking. It was at 3 level, and we heard a lot about integrand. So this is another direction we might go. It was talking about NLSM or all other theories. It's a leading order in this expansion, and there are higher orders. Given the symmetry, of course, we can study also in this direction. What is sometimes not discussed very often, but we know from QCD there is something like anomaly responsible, for example, why there is a pion to 2 gammas decay, a very important property. So it would be nice. Of course, there is no reason whatsoever to see it from bottom up. I mean, it's coming from up. On the other hand, it's in the amplitude, starting, I don't know, from I think 8-point amplitudes at OP6 or OP8. I'm not sure. Amplitude mixes with the NLSM. So is there some way to? Is there some property which would need this anomaly present? I mean, I don't think there is an answer to this. Of course, you can study anomaly by independently, but it would be really nice to see if there is some natural way. And of course, geometrical picture, and after all, this is a conference focused on geometry. This is our biggest hope, that we would be capable to extend all geometrical knowledge we have from other theories. Also, it would be possible to extend it for NLSM, and we are hoping, especially with Johannes, that we will be successful. So let me, for example, show you a little bit, because I think it can be shown in 1 or 2 pages what we did about these higher orders. So we are really connected with so-called chiral perturbation theory, which is a phenomenological theory of low energy QCD. It means that the leading order should be the NLSM. So far we focus on this term OP2. This is our NLSM, but you can do the study of the high order still for the massless case. So these are the number of terms which you should study. So I put yellow, this 1, 2, 2, 3. These are these 4 point of OP2, 4 point of OP4. There are 2 terms of OP6, etc. Because I think I will show them later in some table. So we recently with Shruti and Yara and Yara students, we asked the question about so-called BCJ bootstrap. So as you might have asked, why Adler 0 was used as a defining property. So this is the partially answer to this question, whether we can do something like BCJ bootstrap. BCJ is the relation which also QCD amplitude satisfied, and we asked this NLSM satisfies this property, but of course, higher orders, they don't necessarily satisfy it. So we ask what happens if we want this important relation be satisfied with higher orders. And this table you can find in the answer. So these are 1, 2, 2, 3. I put in yellow just to connect it with this table for 4 points. So this is the order, and these are this number of possible monomials, number of possible terms we can have. And it's very simple. Take the 4 point. You have the amplitude and apply the BCJ and ask how many constants survive this. And it would say, fine, this is okay, this is the answer. But the most important outcome of that article was that it's not the final answer. Why? Because these are only 4-point amplitude. You can still put them as a sub-amplitude as a vertices to 6-point, 8-point, etc. And still you should satisfy BCJ. And it will somehow kill many of the relation and give you some, so there is one example, it will tell you that this constant should be somehow related, so it's not, there is zero in the sense that it's not a new constant which is entering this order. So the question is, what is this solution? What are this theory? So of course, NLSM is one solution. If you put all them equal to 0, you have NLSM. And there is another beautiful theory, Z theory, which also satisfies it. It's interesting, we don't know any other solution, so it will be interesting to see some non-trivial extension from these two solutions. So I mentioned the Z theory. I will do only one slide. If you have a question, what is it? Or if it is not enough, this information, please ask JJ. He will be very happy to explain you all the details. But I think it fit very nicely here because I started with NLSM, but there is another direction in particle physics, or should I use particle physics, in theoretical physics, string theory. And it's not very well, probably sometimes it's forgotten how string theory was born. It was motivated by explaining the hadronic properties. So it was built mainly to describe pion scatterings and understand the hadronic models, to understand dual hadronic models. So Veneziano amplitude was there for this. Koba-Nielsen formula might be say it's an extension of to higher multiplicities, and in this direction, Z theory is generalization of Koba-Nielsen to give you another ordering. So it's an interesting theory, and as I mentioned, it has a nice this BCJ property, and this is a summary which I try to say in words. So this is a Euler beta function. It's basically this. So why I'm mentioning it here? Because it's a theory which has this alpha prime coupling as single coupling. So we had these tons of constant in chiral perturbation theory, or as I saw, this number of terms. And we have here the candidate to explain the dynamics of pions, which express all those infinite number of constants with only one parameter. So isn't it time to ask whether, okay, finally string theory shouldn't be used also to explain the hadrons phenomenology? And people would say, of course not, because there are several possibilities how to do these stringy extensions, but it seems that there is one interesting focus point, or one interesting, where do they all agree as far as I saw, maybe JJ can correct me, that at next to leading order, they should vanish. And the usual answer is, but this is not seen in the phenomenology. But so for the purposes of this conference, I really look back what is like the last serious study of phenomenological study, how to fit this OPE, it means these OP4 constants. So if you remember, I showed two constants. So how it is possible, there are so many. So the reason is that we have simplification. We are still in the massless limit, and we are in this large NC limit. We have only one trace. So it would then end only in two constants. But what is the interesting thing here to stress? So there is some LA. It's not important. It's a combination of L1 and L2. It's due to mistake of Gasser and Leutwiler because they didn't choose very wisely this canonical form of the next to leading order Lagrangian. So there are really eight constant in SU3 Karol perturbation theory. And for example, here this L4 is this subleading in large NC. So if they do so-called free fit, it doesn't seem that it satisfies this large NC hierarchy. So in their main fit, they put it to some value where they think it should be. So I'm just saying that data doesn't like the idea of large NC, or you might say they all should be like 0. So this is just my side mark, but don't take me seriously. But I'm just saying that it's not that clear from the phenomenology that it's not true that OP4 are somehow all subleading. Sure, Shruti.
Sorry, which are the coefficients that should, in principle, survive for large NC?
Okay, so it's more. So what did they do? The Cayley-Hamilton relation. So if we are in a 3-flavor case or 2-flavor case, not in generic NF, as we are studying this cyclic amplitude, we assume that there are no relation among generators, so we are in generic in a large NF case. So there is so-called L0 term, which for some strange reason Gasser and Leutwiler decided to express using Cayley relation. So they exchange one trace operator, which should be dominant, then exchange it to subleading terms. So they completely, by this choice, they completely devastated large NC. So it's not very easy to look. But so this is exactly why there is hidden large NC suppression. But so for example, I think it's somehow hidden in L1, L2, and L3. So there are two, but there is some relation among them. So I think it's 2L1 minus L2, which by the way is LA, but this is the reason why they have it to check whether large NC is invalid, is one of our selection, and L3. But I don't remember exactly. And the last, I have still 6 minutes. There are still many surprises. So as you probably heard, Nima and collaborators last year, 2 years already, they came to a very surprising connection with, I would call it simplest model for scalars, trace 5 cube theory. It sounds complicated, but this trace means it's simpler. So we are really focusing only on single trace operators. So if you are calculating ST and U channel, you really should take only the cyclic diagram. So if you want to calculate these 4-point amplitudes, it's only propagator because vertex is 1. So you have 1 over S and 1 over T or U, depending how do you define ST and U. So I was a little bit, I lied that we don't need new parametrization. So there is this Xij parameters, but fortunately already heard. It was already defined here. So it's due to the fact it should help you to pick the pick the canonical form, because we know we have if you use ST and U, there is still a condition among them. So this is the way how you naturally pick the one possible choice. So this in this dual graph, it's clear. P1 plus P2 square is x13, and P2 plus P3 is x24. So it's this diagonal which can be easily exchanged. But there is one-to-one correspondence basically between usual pi.pj and this xij. And so there is this trace 5 cube theory. This is very simple to calculate. There is very simple algorithms to give you the result. And where is the connection with NLSM? The connection is the following. So this is the result of 4-point calculation, and the magic is so-called odd-even shift. So this is odd-odd, this is even-even, and of course for higher multiplicity you can have also even-odd. So if it is even-even, you add delta. If it is odd-odd, you subtract delta, and if it is even-odd, you don't do anything. And now the claim is, if you expand the momenta for large delta, so this explicitly for this 4-point, you end up with NLSM. So it's, for 4-point, it's not such a big deal, but the surprise is it works for all multiplicity. So here is the summary that it can be, it works for all multiplicity, it can be extended to loop level, masses can be added naturally. We also hope it could be extended to higher orders, and as you probably also heard, it can be naturally extended for gluon. So this pure NLSM or even this trace 5 cube theory has all this information to glue amplitude as well. And the origin natural explanation comes, no surprise, from string theories. And again, we hope that it can help us to understand the geometrical structure for all the ingredients and NLSM, especially for NLSM. Okay, so this is my last. This is my summary. So I would say NLSM is still full of surprises. So I try to convince you that amplitude methods are important to uncover hidden structure, and we did this bet 10 years ago, 12 years ago. It's also possible for this low energy QCD, and I hope I convince you that it's indeed the case. But I'm hoping that probably now it's time that string theories should pay debt back to this low energy QCD hadronic spectra, and maybe it can be taken seriously also for phenomenology. So this OP4X, it was used some 20 years old data, and there are new data coming from CERN experiments, so there will be also push from the experimental side, and it is definitely, I would say, it is definitely worth trying to look and take it seriously. Thank you very much for your attention.
Okay, thank you. Questions?